In this video, we're going to go through steady state approximation. All right, so let's take a look at this first example. So we have a mechanism here, and remember, a mechanism is kind of like our recipe, and we have two steps, two elementary steps. Okay, so in this example, we have an observed rate of K times the concentration of A squared times C. Okay, now looking at the two steps, we're told step 2 is our slow step, step 1 is our fast step. Okay, now normally with a slow step, if it's not the first step, to find your rate, you would have to add any steps before the slow step to the slow step and then cancel out intermediates. But there's a little curveball here because this is at equilibrium. Okay, so because it's at equilibrium, it presents a new challenge. Okay, so let's take a look at the two steps and notice that we have B being produced in step 1, and then in step 2, B is needed to combine with C to make D. Okay, so B is an intermediate because it is produced in step 1 and then it is used up in step 2. Okay, now here is the curveball with equilibrium. Okay, so B is being produced in step 1 in the forward direction. So when the reaction proceeds this way, B is being produced. But then B is also reforming into A plus A in the reverse direction. Okay, so B is being produced in step 1, and then it's being used in step 2. Step 2 is the slow step. So basically B is being made, and we have this large stockpile of B, and we use a little bit of B at a time. So pretty much our stockpile in B is going to be the same because it's being produced very quickly, but it's not being used up very quickly because step 2 is the slow step. Oh, look at that steady state. You see? Get it? All right. So let's go through how to verify our rate here. Okay, so we already established that B is an intermediate. Okay, so what we're going to do is we are going to write out our rate laws. So for step 1, in the forward direction, we have K1. So first step, forward direction, is going to be K1, and then our rate would just be A squared. Okay, now in the reverse direction, when our equation proceeds in the reverse direction, our rate would be K negative 1. So we indicate the reverse direction as negative 1, and then we just have B. Now I'm setting them equal because step 1 is happening at equilibrium. So the rate in the forward direction is equal to the rate in the reverse direction. That's by definition what an equilibrium reaction is. Okay? Now, B is our intermediate, and that's going to be important. So let's rearrange what we just wrote to get B by itself. Okay, so to do that, I would divide both sides by K minus 1. Okay, so on the right side, that would cancel out, and I would just be left with, let me erase this actually, I would be left with B is equal to K1 times A squared over K minus 1. Okay, now the second step is our slow step. So if I wrote out my rate for the slow step, it would be K2, and it is 2 because it is the second step, and it would be B and C. Okay, now we just solved for B. We solved for the concentration of B. So this is going to get a little messy, but I am going to substitute this in for B. So let's do that. So we're going to get rate equals K1, K2, those are in the numerator, and then A squared, that's C right there, okay, and then in the denominator is going to be K minus 1. Now we're able to do something kind of cool here. All of the k's are going to combine into a single k. So we'll just be left with k, a squared, and then c. And would you look at that? It matches up with our observed rate right here. Okay. So in this case, like if we had just done what we had previously done, where you kind of like cancel out the intermediates, it would kind of match up with what we would normally get in this case. But again, the reason we had to go through all those steps is because that step 1 was at equilibrium. Okay, so you have to kind of go through these extra steps to verify the rate when you have an equation that's at equilibrium. Okay, so we just kind of did that, and let's move on to another example here. Okay, so same thing. Let me add a page here. Okay, just so we have some more space to work. Okay, so in the second example, it says ozone naturally decomposes into oxygen according to the following reaction. So we have our overall reaction, 2 steps, and our observed rate. And the question says, which is the rate limiting step? Well, if you look at the 2 steps, if it was step 1, for example, if I were to write out my rate for step 1, let's see, rate equals K1, and then it's just O3 on the reactant side, so it'd be O3. That is not that. So it can't be step 1. So it's got to be step 2. So step 2 has to be our slow step. That would mean that step 1 is our fast step. And just like in the previous example, we have an equation at equilibrium, or reaction at equilibrium. So we're going to have to go through some extra steps here. All right. So when we get all done, we should end up with a rate that matches that. Okay, so let's do this. So let's write out step 1, forward direction and reverse direction. So in the forward direction, it would be K1. And then going this way in our reaction, the only reactant is O3. Okay. Going in the reverse direction, our reactants are O2 and O. So I'm going to set that equal to the reverse rate constant, and then we are going to have O2 and O. O is our intermediate. So we need to solve for O. So let's rearrange this to get O by itself. So I'm going to divide both sides by K minus 1 and then O2. So these will cancel here, and we'll just be left with that. Okay. So let's write out the rate for step 2, because step 2 is the slow step. So that would be K, oops, I want to do my cool purplish pink. So K2 equals, so going this way in the reaction, because it's only one direction, we have O and then O3. And just like in the previous example, we are going to substitute this in for O. Now, this is why I added another page, because it gets a little messy here. All right, so let's write this out. So we have K2 equals, I'm going to write in green what I'm substituting so you can see. So we've got K1, O3, and then K1 is in the denominator, and O2 is in the denominator. Okay, and then let's see, that's just what we substituted in for O, and then we have, oops, I meant to do pink here. O3. Why are we drawing shapes? Let's try this again. Okay, O3. And this is for K2. Actually, this should be written like this. There we go. Okay. Now, let's see how we can simplify this. So we've got K1, that should be -1, and then K2. Those are all going to combine into K. So let me rewrite that. So we have K, and then we have O3, we have O3, and then we have O2. We can simplify this even further by combining the O3s. So we'll end up with K O3 squared, and then O2 in the denominator. And would you look at that? It matches up with what we have here. So we must have done something right. Okay, so just a quick recap. You only need to do this when you have a step that is at equilibrium. Okay, so the only reason we were doing all this work is because we had a step at equilibrium. Okay, so you use this process to go through and verify to make sure that everything is where it's supposed to be. Good luck and have fun.